So I'm remaking this video about an introduction to Pytorch because I seem to have lost the video that I made. Okay, this is just going to be a quick introduction to Pytorch, specifically the tensor uh, data type in Pytorch. Let's go to Google Colab. And once you go to Google Colab, you want to make a copy to drive, which will make a copy of the uh, Google Colab notebook to your Google Drive. So this line is just something that you do to make sure that matplotlib plots are plotted within MATLAB. So let me run that. It doesn't do anything for this and actually a few other notebooks that we're going to look at. But I think the final notebook that we look at has plots and they will appear in line. Let's run this. Import torch is the primary um, uh, import for using PyTorch. This is something you want to put at the top of your notebook, Python notebook. You can check what this from future import print function is. You can check its usefulness by commenting it out and so on. Okay, so let's actually look at some simple commands in PyTorch. Let's run this thing. You will notice that what we're defining as I run this thing, it says x equals torch dot empty 5 comma 3. This is very similar to NumPy arrays. So recall we had NumPy dot empty 5 comma 3, and it would create essentially a 5 comma 3 matrix with what looks like random numbers. And then we can print that matrix. However, instead of array, it actually says tensor. And they explain what tensors are here. Tensors are essentially identical to NumPy arrays for our purposes, and NumPy ND arrays. Oops. NumPy ND arrays, except that tensors are also useful in the context of GPUs. So what PyTorch has done is essentially create a new data type / class called tensors, which for all practical purposes are n-dimensional arrays, except you can access them and manipulate them on a GPU. So it's kind of a port of ND arrays to GPUs, okay? But a lot of the syntax and a lot of the functionality of n-dimensional arrays are there in tensors as well. And then here we are just having a 5 by 3 matrix that is of the tensor data type, okay? If I recreate it, well, the numbers remain the same, I suppose. Okay, so this is an empty matrix. Even though it's empty, some random numbers get assigned to the various elements. So you should be very careful that if you initialize an empty matrix, it's A, not truly empty, and B, the random numbers that you see are not really random and not necessarily following a particular distribution that you can control. So if you really want a random matrix, you should use torch.rand. And this will now create a random number matrix. You can check what this function does. You can just say torch.rand. And it's numbers drawn from a uniform distribution on the interval 0 to 1. What that means is, well, if you do a histogram of each of the elements, the histogram will be constant. In other words, every number between 0 and 1 is equally probable. And then you notice that the brackets here are square brackets here and round brackets. When we display an interval 0, 1 with these different brackets, the square bracket means that 0 is included in the interval, and the round bracket means that 1 is not included in the interval. So if you generate random numbers using this function, 0 might occur occasionally because it is included, but 1 will never occur because it's not included. Okay. Okay, so that's rand, and we just created a 5,3 random number matrix, which is of the tensor data type. We can also, just like NumPy, create a matrix of zeros, 5x3 matrix of zeros. Here we have explicitly specified the data type of these zeros. Let me delete this thing, and you will notice that these zeros will acquire a dot. What this dot means is that they are sort of floating point double precision numbers. But if I undo, command undo, what this torch.long means is that we are specifying the data type of these zeros to be long integers, which is a specific data type. I hope people cannot hear the noise outside my house. There's some truck that's going back and forth for some reason. Okay, so anyway, so that's how you create a matrix of zeros. By default, for most of our purposes, we will not necessarily be specifying the data type. We'll just assume everything is floating point double precision numbers. Just like ND arrays and NumPy arrays, we can define a torch tensor by actually specifying a matrix. Here is a 1 by 2 matrix, 5.5, 3. So it's 1 row, 2 columns, I suppose. And we can print X. And then we can do the same. I guess if we want, we can do this. Okay, so let's see if that works. Okay, so that's a 2 by 2 matrix we just created, and so on and so forth. We can do, here's an interesting one. So just like zeros, there is a command for ones. It's called x.new ones. Okay, and we can delete this. So this, we already have x, and then we are replacing that x with a 5,3 matrix of ones. And then this is kind of interesting. Here, what we're doing is we are overwriting this x matrix with a rand_n matrix. Rand_n generates a matrix of random numbers which are normally distributed. And this is doing floating point data types. Doesn't matter. But more importantly, there is this rand_n underscore like. If we had just said rand_n, it would just create, and then we can give it this size. It will, so we could have done something like y equals torch dot rand_n 5,3. That works, and then we can do print y. And that will create a 5,3 normally distributed random number. So that's y. So this x, which I'm going to actually call z for now, print z. I'm going to actually change the variable name. So z is also a 5,3 random number matrix. So, but how did Torch know that it had to create a 5,3 matrix? So because the input is x, this underscore like function, random underscore like function, essentially makes a new variable z that has the same size as x. Okay, so this is easily done in MATLAB as well. Let me show you the MATLAB version, which I'm sure we've done in many of our codes. Um, so if we have, I don't know, x equals 1s, 5 comma 3 in MATLAB, for some reason it's being a bit slow, but then we can go z equals random, and then we cannot really say x, but we can say size of x. Oops, size of x, which means that MATLAB will create a random number matrix which has the same size as the x matrix. So that's what this underscore like does. Instead of passing the size of x to Torch, you can actually pass the matrix itself, and then it'll create something that has the same size. We could have easily done just gotten the size of x and then plugged it in here. I guess for some reason they chose to provide a function that does this thing. In any case, so this, I think, given that we've changed things, this is what we wanted to do. Okay. Here are some additional commands. I suppose we create a new variable y. I guess we've already done that here, but we can create a new variable y. X is already a 5 by 3 matrix, and then you can do print x plus y, prints x plus y. This is interesting way of a different way of addition. If you go torch.add x comma y, it creates x plus y essentially as a new tensor. That gives you exactly the same answer as this. This is yet another version of addition, where if you first define a matrix result, which is an empty matrix, you can go torch add x comma y out equals result, then the sum of x and y gets assigned to result, and then you can print result and you get exactly the same thing. Okay, just different ways of doing the same thing. This is interesting, where let's say you wanted to add x to y and then take the new result and assign it to y. In other words, you go y equals y plus x. That can be accomplished as y dot add underscore x, and then what happens is y, the value of y changes to x plus y, okay, which is this thing. I suppose we could have done this as well, we've already changed y, so I guess we cannot really. I was going to say we could have done this as y equals x plus y. That would also have worked. Would have given the same answer. Okay. We can do the same NumPy-like colon operation to extract specific rows or columns and so on. So that works. This is interesting. There is a command called view, which reshapes a matrix or a tensor. So in MATLAB, there's a command called reshape. Z. So Z is a 5 by 3 matrix. We can, for instance, reshape it into a 15 by 1 matrix. That's a 15 by 1 matrix which has the same elements as Z, taken in this order. First column, second column, third column. First column is here, second column is here, third column is here. So it just rearranges these elements with this output size. Okay. So that's reshape, and then Python, specifically Pytorch, It's done using this command called view. Um, so let's look at that. So we've just created here a random number matrix 4, 4. So it's got 16 elements. And then if you go y equals view 16, it will basically rearrange the 4 by 4 matrix into a 16 element one-dimensional array or tensor. So let me, and then they are printing, and then Z, they're rearranging with 8 columns, and then they give -1 as rows, which I find not very, let's say, clear what that means. Really, what that defaults to is 2. So if you say 8 here, and then put a -1 here, Python/Pytorch infers this element to be 16 by 8. So whatever needs to go in here so that the total elements of this new matrix is the same as the total elements of the old matrix. Just a weird shortcut syntax, but I feel like some of these shortcut syntaxes are more confusing than perhaps obvious. But so if you're a beginner, maybe I would avoid using these shortcut syntaxes. So I'm just going to print x size, y size, and z size separately so that they are on different lines rather than in a single line like this. So x is 4 by 4, y is supposed to be a one-dimensional array with 16 elements, z is supposed to be also a two-dimensional array but with 2 rows and 8 columns. Okay, let's look at those things. So this is the size of x, this is the size of y, this is the size of z. And then we can print the actual matrices themselves. We can go print x, print y, print z. Okay, let's just print those things. So this is x, this is y, okay, so, and this is z. Notice the y and z look similar, but they're actually different. So y looks like 0.2930, 0.2911, etc. And then there's a comma here, and then things continue on the next line. So this is, it's not like this is the next row. It's just a single long row, and they've just written it on the next line so that, well, they don't keep writing it here. Whereas the z variable, it's different from the y variable. There's a close bracket here and then a comma. So this is the first row, and then this is the second row. So there's a difference between y and z, as can be understood from the size itself. Okay. The other thing I wanted to mention is I'm forgetting what I wanted to mention here. Okay. So in MATLAB, reshape actually pulls, rearranges and constructs this new matrix from the original matrix column by column. Okay. So the new matrix is obtained by taking the first column, filling in the column here, and the second column, filling in what comes next, and so on and so forth. Whereas in Python, it happens row by row. So the reshaping, you first go along here, and then go along the second row, and then fill in the elements of the new matrix row by row from the original matrix as opposed to column by column. So that's a difference. Of course, you can reshape it to any new matrix as long as the new matrix has the same size as the old matrix, same number of elements as the old matrix. So we can go 3 and 3, 5 here, and it'll create a 3 by 5 matrix. Again, things are derived column by column. So these 3 are these 3, and then you take this element, and this element, and put that in the second column here, and so on. Okay, that's how things are reshaped here, and things are reshaped row by row here. Okay. Um, so that's reshaping, and that's very useful if you want to reshape some input matrix in some, as we will be using later on. Here's another little command, x.item. So we first create this matrix or tensor, um, torch.random of 1. Um, this is just a single number, but it is of the data type tensor. Okay, so it's of the data type tensor. So if you want just a real number, then there is essentially a command called item, which allows you to convert this tensor into a real number. Okay, um, I suppose that's that. Okay, this is a tensor. This is a real number, or essentially a floating point number. Um, and sometimes it's useful to convert one to the other. Sort of analogous to this, they provide um, a NumPy bridge. In other words, these are Pytorch tensors, which, like we said, are very closely related to n-dimensional arrays in NumPy. But then you can convert one to the other. If you have a Pytorch tensor, um, so that's a tensor, and then you go b equals a dot numpy, gives you essentially a numpy array here. So it's been converted. So even though it looks similar, b and a are the same, they are different data types, but containing basically the same values. You can do the same thing here. Okay, this is always a weird one, where when you say b is obtained from a, and then you add a number 1 to a, b also changes, unfortunately. And that's something you want to be very careful. I think, as we discussed when we did NumPy as well, rather than equate it, maybe you want to copy over a new variable, create a new variable that is different from the old one. Okay, let's see if this works. So because I added a 0 to it, b is no longer associated with the memory location of a. And then when you add 1 to a, b doesn't change any longer. Okay, so just doing that little thing, make sure that b is not tied to a. Okay. And then there's another little example, I guess, where you're converting a NumPy array to a torch array. So you can create a NumPy array using this, like we did in the previous videos, and then you can convert that into a torch tensor by doing torch dot from NumPy a equals b. Okay, so that is it. Something I wanted to mention, and I think I may have mentioned in the previous videos as well, in other contexts. Let's go here, and let's just go x equals, I suppose, torch dot random 5,3, and then we go to the next line. Once you've run that, you go to the next line and then go x dot. It tells you all the different commands that you can sort of operate on x. Okay. So you can go print x, and then x dot, let's go print x dot abs. Let's try that. So what happened was this X matrix was this matrix which had some positive numbers and some negative numbers. And then when you did x dot abs, you just got the absolute value of that particular variable. Let's see what else is there. As soon as you press the dot, you'll get all these things. Arc cosine. If you want to take the inverse cosine of x, that's what you get. Okay, you get NaN, which means not a number. Why do you get an NaN here? Something to think about. Arc cosine is just cosine inverse. Cosine inverse of a number between greater than 1 will be not a number. Okay, cosine of anything is between 0 and 1 if that anything is a real number. So if you ask for inverse cosine of a number greater than 1, you'll get not a number. Technically, it's a complex number, but I suppose when we have tensors where the elements are real numbers, essentially, yeah, it comes to not a number. Okay, so that's pretty much all we are trying to do here. Like we discussed, it's almost identical, a lot of these things, to Python's NumPy ND arrays or n-dimensional arrays, except there are some additional functionality, as well as there is ability to use these tensors on GPUs. And that's the final little piece here. CUDA tensors, it says. Okay, so this is just doing everything except on a GPU. CUDA is a programming framework for NVIDIA GPUs. NVIDIA is a company that makes GPUs that are popular and powerful. And then CUDA is a programming framework for that. So MATLAB can interact with CUDA. Pytorch and Python can interact with CUDA and so on. This is a way of programming or communicating with GPUs. Let me run this thing. So what they're trying to display here is a way to do z equals x plus y, except we do it on a GPU as opposed to the CPU. Let me run it, and it will give you an error here. Maybe not. It doesn't give you an error, and that's because there's an if-then statement here. It says if torch.cuda is available, then you do this. So we can check whether that was true or false. We can go print that. It's false. Because it's false, these things were never run. Basically, it's saying CUDA is not available, so don't run it. So CUDA not available just means that GPU is not available. We may have done this already in a previous video. If not, we see this right now. We can change the runtime setting. So there is this thing called the hardware accelerator, and it's on none right now. We can select GPU. It says to get the most out of Colab, avoid using GPU unless you need one. Learn more. You can click through that. They talk about why you should not use GPUs unless you really want to use it. Basically because a million people are using this free service, and you don't want to slow the GPU down unless you really want to use the GPU. In any case, let's save this thing. Now, let's run this. Now we might get an error. Okay, so we are getting some kind of an error, and it says name torch is not defined. So we made CUDA available. We made basically GPU available, but something is wrong. It's not able to recognize or use the GPU properly. And the reason is because initially GPU was not available, and we loaded Torch for essentially CPU by default. So what we need to do is, after having changed this runtime to GPU, we have to run specifically import Torch again so that the GPU version of Torch is imported. We can skip all this stuff because this has mostly been a scratch pad. Now I think we can run these things. So we are creating y from scratch, but looks like it requires x. Um, Let me just define an x here. Something. We've defined x here, and then y is the same size as x, except it's a matrix of ones. And then this command essentially pushes the X matrix to device, where device is CUDA. Basically, we're pushing the matrix to the GPU. And here we are creating Y with the same size as X, and then we are creating it on the device, namely the CUDA device, which is the GPU again. Uh, and we're creating Z, which is X plus Y, which automatically gets processed in um, the GPU, because both X and Y reside on the GPU. Z is computed on the GPU. You can print Z, and then you can push Z back to the CPU. So you're sort of pushing information from the CPU to the GPU and vice versa. So let's see if we can run this thing now. It's very slow. And when it's on the CUDA device, namely the GPU, there is this additional annotation. But it's basically the same variable. Print Z. This Z is initially in the GPU device, and then it's been pushed to the CPU device. Okay, so that is how one uses GPUs, essentially pushing the tensors to the device, the GPU device, and then once you push all the tensors to the GPU device, you can do calculations on the GPU implicitly. Okay. Here, if we run this again, it will probably be true because now CUDA is available. Okay, and we've in fact already used the GPU. Okay, so that's it for a basic introduction to tensors. We shall do automatic differentiation in the next video.